head of C lab focused on understanding nonlinear stochastic phenomena. Specifically, they study the intricate dynamics of complex systems as collections of agents that form out of equilibrium structures, displaying emergent behaviors such as self-organization and pattern formation. Some useful techniques that they use are to study these phenomena are machine learning and artificial intelligence. With this, they've been able to publish 2 books, Introduction to Econophysics and Machine Learning for the Physical Sciences. Please help me welcome Carlo daCunha.
Got it. Thank you for the introduction. Thanks everybody for coming. So let's talk for the next 1 hour or so about electron dynamics in quantum constrictions, using machine learning, of course. But I would like to start with a provocation. So here we have this beautiful picture. I hope you all can see. Yes, we have this mountain. It could be Humphrey, for example. We have this storm and this trees and beautiful picture, creepy but beautiful. But the question that arises is, how would we look at this picture if we were to use linear physics? It would be something like this, right? So as Benoit Mandelbrot once said, clouds are not spheres, mountains are not cones, coastlines are not circles, barks are not smooth, and lightning does not travel in a straight line. So this research is basically an understanding of nonlinear and stochastic systems. And what is interesting about nonlinear and stochastic physics is this phenomenon of pattern formation. Take, for example, a gas. A gas is something boring. It's amorphous. It doesn't have any structure, just something gaseous. But let's take this flock of birds. You can see here, this flock of birds, the birds interact among themselves non-linearly. So because of this non-linear interaction, they produce these beautiful patterns that we see in nature. You can see the same school of fish, flock of birds, and many other events in nature. So the question is, can we observe the same behavior in electron systems? Well, let's try to answer this question during this talk. So for this first, I'm going to talk about a device that we prepared for observing or try to observe such phenomenon. Then an imaging technique to try to observe the electrons in the structure. And then finally, some machine learning approaches to try to get some information out of these measurements. So let's start with the quantum point contact, the structure that we're going to use to try to observe such phenomena. A quantum point contact, as you can see, you have 2 blue trenches, and the electrons are forced into the red region. And since we have a quantum constriction, the transport or the conductivity through such device is quantized, and you can see there as we increase or decrease the width of the constriction, we see this quantization of conductance. Every time we have a mode passing the Fermi level, we see 1 more quantum on the conductivity. So that's the device we're going to use. Why? Because then we have the electrons well confined in the constriction, they get to interact, and then hopefully we can see something. And how are we going to image the electrons? Using this technique called scanning gate microscopy. How this technique works is the following. We have a charged tip, right? So the charged tip scatters electrons in the device. So if it's on top of a lot of electrons, there's a lot of scattering. We see a big change in conductance. While if it's on a region that has few electrons, there's not much scattering. We don't see much change in the conductance. So by scanning this tip across the device, we can have a map of the electron flow in the device. Good? Excellent. So this is a real picture. Our sample is sitting there. The tips on the top, we just approach, scan, take pictures. If we apply some basic first order perturbation theory, yes, we can prove that changes in conductance are exactly proportional to the local electron density. So it's a good technique to image how the electrons are distributed in our device. Question, what would an image look like if we had diffusive electron transport? I know it's a quantum constriction, but what if I had diffusive transport? What would the image look like? Boring, right? Like an error function, a decaying function, something homogeneous, nothing special. But since we are talking about a quantum constriction, we have these beautiful patterns. You see, every time you have a new quantum of conductance, we see these branches in the conductance flow. So there you can see one branch, two branches, and three branches corresponding to different plateaus in the conductivity curve. Interesting, isn't it? Okay, how is the device fabricated? First, we use this very simple equipment. You can see that. A molecular beam epitaxy device. So epitaxially, we grow layer by layer of material that we want. In this case, this heterostructure was grown on an indium phosphide substrate, and then indium aluminum arsenide, indium gallium arsenide, such that we can create this shape for the bottom of the conduction band. This is the Fermi energy, so we have a small potential well. So we can create a two-dimensional potential well right there on the top, something like 30 nanometers below the surface. So with this, we have a two-dimensional electron gas. On this structure, we do some etching, we do some metal deposition, and then we create this whole bar structure. So this is etched. The cyan color is a mesostructure, and then we have gold pads contacting the whole bar structure. Good. So we started with a two-dimensional electron gas. Now we have a whole bar structure, and then on top of this whole bar structure, we do electron beam lithography and create the quantum constriction. So by probing different electrodes in the device, we can, for example, apply current, measure voltage, or measure transversal voltage drops, and so on. It's a very flexible device. Characterization. So first measurement we did was Shubnikov-de-Haas measurements. We apply magnetic field perpendicular to the electron flow. So this creates Landau levels. Every time the Fermi level passes a Landau level, we see an oscillation in the conductance curve. And from this, we can extract a lot of properties of the device. For example, we can extract the carrier concentration. The carrier concentration in this case was 7 times 10 to the 11 per square centimeter. The mobility, 7.4. What is interesting here is that the mean free path, given this carrier concentration and the mobility, is only 1.2 micrometers at 300 millikelvin, sorry. So when we lower the temperature, right there at the bottom, the mobility was supposed to be very high, but it's only 1.2 micrometers. Can anybody tell me why? Defects. A lot of defects in my sample, right? If my sample was clean, the electrons would go a long path before scattering. But since I have a lot of defects, the mean free path is only 1.2 micrometers. So I have disorder in my quantum well. If I squeeze my constriction and measure the transmission or the conductance, I get this weird curve. I was expecting some plateaus, right? But I get this strange curve because of impurities, disorder, defects in my sample. That's not something bad. It's actually something very useful. You'll see why in a minute. When we take the fluctuations of the transmission curve, the fluctuations of the images that I'll show you later, the fluctuations of the Shubnikov-de-Haas measurements, we get this distribution. This one right here. This is a typical image. These are the distribution of the fluctuations And what we see is this interesting Gaussian shape. Why is this interesting? Well, if the transport was diffusive, ballistic, then I would have a Poisson distribution. But no, I get this Poisson-like distribution, which implies that a transport in my structure is chaotic. I have quantum chaos in my device. So that's why it's so interesting to have impurities, defects, because I can see chaotic quantum transport in this structure. Exciting. If you're interested, for every kind of measurements I show you here, you can do a QR scan and see the paper. This was actually the cover of one applied physics letters some years ago. Let's continue. So here it is. Images of chaotic electron flow in quantum constrictions for you. The voltages you see here are basically how much I'm squeezing my constriction. So by squeezing the constriction, I can change the image. I can change these patterns of electron flow, and they all correspond to chaotic quantum transport in this structure. Amazing. So the question is, okay, nice, but what is creating this quantum chaos phenomena? By the way, what is quantum chaos? We know chaos, right? Sensitivity to the initial conditions, but in quantum mechanics, we don't have initial conditions. So what is quantum chaos? Is the quantum dynamics of classically chaotic systems. But let's proceed. What kind of potential is creating this quantum chaos? I know that I have impurities in the sample, right? I know that I have defects. The mobility is very low. I can see these patterns. I have quantum chaos. I can see on the measurements. But what is creating the quantum chaos? Well, that's not something very simple to obtain. I have these images. That's all I have. How can I image the potential? I can't. It's a two-dimensional electron well below the surface. I have to do it indirectly using some advanced techniques. For this, I'm going to use machine learning. It's a hot topic. Everybody loves it. So let's use it for something useful. It's an inverse problem. I have the scanning gate microscopy images of the electron flow. So from this, I want to do the inverse problem. What is the potential that is creating these images? I know how to go from here to here. I take Green's functions, I calculate the Green's functions, I apply perturbation theory, I can use many methods for moving from here to here. But how do I go the opposite way? Machine learning. I tried several machine learning techniques. The first one was the beautiful peaks-to-peaks, GAN. Have you guys seen this before? Peaks-to-peaks, GAN. GAN stands for Generative Adversarial Network. It's used to create fake images. The idea is this. I have the scanning gate microscopy image. Then I have a nonlinear array of elements, neurons, as the computer scientists call it. One network is trying to produce something corresponding to the potential, the network up there. Here I have real potentials obtained from theoretical measurements using Green's functions. And then I have a second neural network that is trying to say if this image is real or fake. So I have a competition between two networks. One at the top is trying to foolish this one, and this one is trying to learn if it's being foolish or not. So this competition creates a very interesting network capable of producing very realistic results. For example, this is created using pix-to-pix GAN. This is the original picture. Then we train the network to do exactly the same, but trying to produce a zebra. And it does beautifully. Second technique. Well, it's a problem in nonlinear physics. So why don't we try to use something nonlinear? Well, neural networks are nonlinear, but something more explicitly nonlinear. Let's put it this way. In this case, I use the cellular neural network. Here, again, we have neurons, nonlinear elements. They communicate with each other using this very simple expression. Here we have some tensors, cloning tensors, etc., but we process it over and over and over again, such that this cellular neural network has an attractor, which is what I'm looking for. Does it make sense? It's a dynamical system. Okay, so I apply this, I train this network with theoretical density of states, theoretical measurements, and then I try to learn it to the experimental measurements. And the third technique, a much simpler one. Again, we are dealing with nonlinear stochastic systems. Let's try to do something similar. Evolutionary search. Evolutionary search is something that we see every day just looking at nature. For example, flocking of birds. People usually think that there's a leader, but no, there's no leader. The only mechanism necessary to obtain this flocking behavior is that each bird tries to stay more or less on the average in regards to their neighbors. If we just apply this rule, then we get a flocking behavior. So let's try to apply the same idea to our problem. Instead of birds, we have potentials, right? We evaluate if they are good enough using Green's functions. We give rewards to those potentials that produce images of electron flow more similar to the ones I have obtained experimentally. And then I do it over and over and over again until it converges to something meaningful. Simple, elegant. Let's see what we obtain for the results. But before I show you the results, what technique do you expect to produce the best results? We have three: pix-to-pix GAN, we have cellular neural networks, and we also have swarming evolutionary approach. Which one do we expect to give the best results? Hold on for a moment and let's see the results. Okay. So here I have a scanning gate microscope image, left top. That one, right top, was obtained using pix-to-pix GAN. This is obtained using cellular neural networks, and this one is obtained using evolutionary search. These are three results using three different methods for the same image. That's the original image, and these are estimated potentials using three different techniques. Can you see which one is better? This number right here is the image entropy. It basically tells us how much information is contained in the image. So CNN and evolutionary search produce images with more or less the same amount of information, but GAN produces images with not so much information. Let's continue. What about potential roughness? The potentials obtained are rough, right? And they are supposed to be rough because I have disorder. This one right here is GAN. The x-axis is basically the width of the constriction. So depending on the width of the constriction, I have more or less the same roughness. But right there on the top, it's CNN and evolutionary search. They're more or less similar, but evolutionary search has less variability than CNN. Can you tell which one's better? Difficult. Let's continue. Fractal dimension. My images have some kind of self-similarity. So I can ask, what is the topological dimension of these images? That's something very easy to measure. You just take the number of copies as a function of the amplification I'm applying. If I calculate some blah, I obtain topological dimension, in this case, the Hausdorff dimension. This is a Sierpinski gasket. In this case, the dimension is 1.5. We're used to something like one-dimensional, two-dimensional, but when I have self-similarity, dimension is fractional. Well, let's compare the techniques. Again, pix-to-pix gun produces this with a lot of variability. But right there on the top, CNN and evolutionary search are more or less similar, close to 2. The images are close to something two-dimensional, whereas the potential estimated by pix-to-pix gun is something fractional. Okay, let's talk about grain distribution. When I have some potential, I can draw the boundaries, then I can study the area or the number of regions with similar areas. The mathematics is here for you to see, something simple. And we obtain this. Now things are a little bit different. Okay, CNN and pix-to-pix gun have similar results for surface roughness, but evolutionary search gives me something way different. So this is the grain size on the x-axis. So this tells me that the images produced by evolutionary search have a lot of noise, very small grain sizes, right? So a lot of noise. On the other hand, the bore radius for my samples is in this region. Evolutionary search gives me something non-zero in this region, but the other two techniques give me nothing. Lastly, the quenched potential. What is a quenched potential? Well, I'm squeezing my constriction, so the potentials change, right? The scanning gate microscopy change, but there are some features that are persistent. They do not change. They are quenched. So if I take 1 over the variance, the pixel variance of images, then I can have an estimate for the quenched potential. Here, I have pix-to-pix gun, something more or less flat. Here I have cellular neural networks, and here I have evolutionary search. Good. So the plot I was obtaining before kind of shows exactly this. I have a lot of noise for the evolutionary search. And the image entropy for images obtained with gun contain much less information, right? So yes, we can see this here too. So let's bring the question again. So what is the best technique? Come on, 33%. Yes, the best technique is evolutionary search. So when we compare the experimental images with the images produced using the technique, we get a correlation of 72% using evolutionary search. But if we compare the experimental images with the images obtained using the other two techniques, the correlation is 10, 15%. So evolutionary search gives us a much more trustable result than the other two. Can you tell me why? Pix-to-pix gun is amazing. They can change a horse into a zebra. So why doesn't it give us good results? Yes. Do you know how long does it take to obtain one image using the scanning gate microscopy technique? 1 day for one image. Then we have to process the images. Do you know how long it takes to process all the images using evolutionary search? 1 year. So it's a very slow process, experimentally slow, theoretically slow. So we don't have many samples. Our training set is very limited. And for evolution, for gun, pix-to-pix gun, we need thousands, hundreds of thousands of samples, which we don't have. So training a neural network with a limited data set gives us biased results. But the question remains, why does evolutionary research work so well if it's so simple? While it's guided by physics, we generate potentials, we select those that are physically meaningful, and we neglect the others. So physics is guiding the process. So it has to give us something more correct. So that's why I obtain something very interesting, very meaningful using evolutionary research. Okay, so in conclusion, yes, we can see pattern formation in electron systems. We can observe quantum chaos directly using the technique of scanning gate microscopy. Yes, we can use machine learning to estimate the potentials that create these patterns of quantum chaos. And finally, evolutionary search is the best technique to use if you have a very limited data set and you want something that obeys physical rules. Thank you very much.
Thank you. We're gonna now start taking some questions. We're gonna prioritize the students first.
So will you remind me for the neural network setup, how you were training it? Was it based off of theoretical stuff? Is that what you said?
Yes.
Is that why your data set was so limited? It's just because it's like, in theory, we should get this. You know, that's
Yes.
okay.
So we use non-equilibrium Green's functions to produce pairs of potential and scanning gate microscopy images. But it's a very slow process, so our data set is not very big.
You need like thousands.
Hundreds of thousands.
Really, really good.
Yeah.
My question was, so you showed that a few slides ago, how the evolutionary method has like a 72%
Mhm.
accuracy. Is that standard? Is that like a good number?
You can claim it's not good, but if you compare all the techniques, that's what gives us the best results within 1 year of calculation. I could go longer, maybe 1 decade, but yeah. We are working on improving the evolutionary search algorithm. We may get something better in a shorter time.
Yeah, as you mentioned, Matt and I are working on a similar technique actually, where we take open stack, but we just take a medium with a microscope. We do the same thing. It's kind of that evolutionary search, and we just went through comparing that we used to populate all of it. Series of people that think the same. Maybe we should talk some.
Of course, yeah.
More questions? Not, then let's take our speaker one more time.
If you have any more questions, just let me know, send me an email.